Welcome back to the Deep Dive, where we take complex architectural landscapes, break them down, and really give you the essential knowledge you need to sound like an expert. Today, we are strapping ourselves in for a truly foundational deep dive into the engine room of the modern internet, cloud compute.
It's true. I mean, for most people, the cloud is still this massive nebulous concept, the deep unknown where your application lives somewhere else and you just hope it scales.
Right.
So our mission today is to move past simply listing off the menu of compute options like App Engine, Cloud Functions, Cloud Run, GKE, Compute Engine, and really focus on the architectural why.
The why, that's the key.
Exactly. Why, when you're faced with a specific business requirement or a technical constraint, do you choose one specific tool over all the others?
Okay, let's unpack this.
Yeah.
Because for so many of you out there, this deep dive is probably your first real foray into making sense of all this complexity. If you are prepping for an architectural review or, just trying to catch up on the field, choosing the right compute solution is probably the most critical decision you're going to make.
It really is. It impacts everything. Your monthly bill, your latency, even how large your operations team needs to be.
So the goal is to build a solid base.
A rock-solid base of understanding. Look, think of the entire compute landscape as a spectrum. If you can understand this spectrum, you're well on your way to mastering cloud architecture.
A spectrum. Okay, so what are the two ends?
On one far end, you have maximum operational control. That's where you manage everything yourself.
And on the other end?
Minimum operational overhead. That's where the cloud provider manages, well, almost everything for you.
So if I just spin up a raw compute engine virtual machine, I'm at that maximum control end.
Exactly.
I get 100% control over the OS, the patches, the security, the networking, all of it. But the trade-off is I have maximum management overhead.
Precisely. You own that maintenance burden. So as you move along the spectrum, maybe toward things like Cloud Functions or Cloud Run, you start giving up that granular control over the infrastructure.
In exchange for
what we call the goal of no ops.
Yeah.
Zero operational work on the infrastructure side. And these incredibly robust auto-scaling solutions that can handle spiky traffic, like instantly.
Got it. And that movement toward serverless is where we're going to start.
Yep. Let's start with the simplest, most minimalist path on that spectrum.
True serverless simplicity.
That's it.
So let's kick off with Cloud Functions. These are, I guess, the purest, most foundational form of serverless compute.
They really are.
They're just delightfully simple pieces of code designed to do one single thing.
I always think of Cloud Functions as the ultimate scale-to-zero utility.
Scale to zero, that's the key phrase.
It is. Imagine your IT budget is incredibly sensitive, and you only want to pay for work when it's actively being done. A Cloud Function is like a highly specialized self-cleaning robot in a smart factory. Its only job is to stamp a signature on incoming packages. Now, that robot doesn't sit there drawing power all day.
No, it just waits.
It only wakes up when the package arrives, does its 5-second job, and then immediately goes into a zero-power sleep state.
That analogy just perfectly encapsulates the core use case, doesn't it? It's all about cost and efficiency.
It is.
Because these functions automatically scale down to 0 instances when they're idle, you literally don't pay anything, nothing, when they aren't processing an event.
Which is ideal for applications or, back-end tasks that have really sporadic, unpredictable activity.
Things that are only needed during business hours.
Right. That ability to scale to zero is the key architectural feature.
Yeah.
It's what drives the cost savings. They're engineered for event-driven workloads, running a small piece of code in response to a specific trigger.
And a classic example is reacting to data storage, right? Like running some code when a new file gets uploaded to a cloud storage bucket.
The most common pattern. Maybe to resize an image or trigger a content scan, something like that.
So if the task is that simple, why is the event-driven nature so important? Why does that make Cloud Functions a better fit than, say, a Cloud Run service, which also offers scale to zero?
That's a great question. For these simple reactive tasks, Cloud Functions are just superior because they are the most minimal abstraction possible.
Minimal abstraction.
Yeah, they strip away nearly all the operational context.
Yeah.
You don't think about HTTP servers or container configuration. You just provide the function code, and the cloud provider handles the entire execution environment, spinning it up instantly based on that external event.
Whereas Cloud Run,
Cloud Run, while it's also serverless, it assumes a more generalized container model. So it includes the overhead of, listening on a port and managing a container image. It's minimal, sure, but it's still more friction than a simple function trigger.
And this high level of reliability and minimal friction, that becomes really essential when we look at more intermediate operational details, things that demand absolute robustness, especially around infrastructure cleanup.
Oh, that's a perfect real-world use case.
Yeah.
It really highlights the shift in thinking that serverless enables.
So set the scene for us.
Okay. Imagine you have a highly scalable backend running on a compute engine managed instance group. These instances are scaling up and down constantly.
Right.
Traditionally, when an instance is shut down, you'd rely on a local shutdown script, something running on the virtual machine itself to clean up associated records.
Like removing metadata or session entries from a high-speed caching database like Redis.
Exactly.
And the problem is, that's not reliable. If the instance is terminated too quickly or the OS fails before the script can finish, those cleanup commands just fail.
Precisely. The Redis database starts filling up with stale records, causing clutter or, eventually, real application errors. That local script running on the instance that's being terminated is just inherently fragile.
The cloud provider might just kill the instance before the script is done.
It happens all the time. Or the script might just fail because of some temporary resource issue.
So how does a cloud function solve this reliability gap?
By decoupling the cleanup process entirely.
Okay.
Instead of relying on the dying machine to clean itself up, we use the event-driven nature of the cloud's centralized monitoring system. We set up what's called a cloud monitoring sink.
And this sync doesn't watch the machine itself?
No, it watches the system-wide cloud logging stream for a specific, reliable audit event.
Like the log message that explicitly says the managed instance group has successfully removed or terminated an instance?
Exactly that one. When that specific log message arrives, the monitoring sync immediately triggers our cloud function.
And because the function runs externally to the instance?
In its own minimal, reliable environment, it can then safely and reliably execute those cleanup commands to remove the stale Redis entries.
So the cleanup command runs every single time, independent of the reliability of the instance being removed.
Every time. It's a fundamentally more robust architectural pattern. You're using the system's own monitoring as the ultimate source of truth rather than relying on the component itself.
That's brilliant. Okay, so that was the specialized robot, the cloud function. But what if our needs are more generalized? We need more capability, and I think that's where Cloud Run comes into play.
Cloud Run is absolutely the natural, powerful evolution of serverless. It keeps all the core serverless benefits we just talked about.
Event-driven processing, lightning-fast auto-scaling.
And that critical scale to zero-cost model, yes. But it wraps all of that around the flexibility of industry-standard containers.
So we're moving from the specialized fixed-function robot to the generalized, fully customizable robot.
That's a great way to put it.
You can program it yourself using any language, any library, but it still just stands by, ready to act, scaling down to zero when it's idle.
The container advantage is the cornerstone here. You're no longer limited to the predefined restrictive runtimes you get with cloud functions or, as we'll see, App Engine standard.
You can run pretty much any containerized application.
As long as it listens on a port, yes. Whether it's a full web app, a complex API backend, or a message processor. This makes Cloud Run an absolute powerhouse for handling that spiky and sporadic traffic that needs a custom execution environment.
Let's talk more about that spiky traffic. A classic use case is processing messages from a PubSub queue. If my application is tasked with, say, transforming financial data, and a burst of 1 million transactions arrives instantly, followed by an hour of silence, Cloud Run is perfect for that.
It is. It scales instantly from 0 to hundreds of concurrent instances to meet that burst, processes the backlog efficiently, and this is a crucial part for cost control, scales back down to 0 without you having to do anything.
No configuration changes from the team.
None. That resilience to unpredictable, massive fluctuations is why it's so often the default choice for modern microservices architecture.
And this mix of container flexibility and serverless management, it also unlocks some really sophisticated deployment strategies. I'm thinking specifically about canary testing, which is notoriously difficult to manage in traditional infrastructure.
Here's where it gets really interesting.
I thought so.
Canary testing is absolutely essential for minimizing risk. It means you deploy a new version of your code, but you only send a tiny, statistically insignificant percentage of your production users to it.
The canaries?
The canaries, right. You observe that subset to make sure there are no errors or performance issues before you commit to a full rollout.
Now, managing that traffic split manually often involves, complex, error-prone changes to DNS or external load balancer rules. How does Cloud Run strip away that complexity?
It bakes the capability right into its core platform design. You deploy the new code as a new revision of your
The
service.
new revision, okay.
Then, within the Cloud Run console or the API, the mechanism is just shockingly simple. You explicitly configure the traffic percentage between the new revision and the current stable one. You might set it to, say, 95% to the current and 5% to the new.
And the platform itself just handles all the underlying load balancing and request routing invisibly.
Exactly. It completely abstracts away that complexity. If the new 5% revision shows 0 errors in cloud logging, you just slide that configuration to 100% traffic, and the rollout is instantaneous and safe.
That's a powerful platform-as-a-service feature delivered within a serverless model.
It really is.
So, moving on to event routing. If Cloud Run is reacting to events, it needs a standard way to receive them, especially when those events come from all these diverse parts of the cloud environment.
That's where EventArc becomes the crucial missing piece. Cloud Run is fantastic, but you need a standardized event routing service that can handle the delivery, the normalization, and the filtering of events from all these different sources across the platform.
The goal is to react not just to external things like HTTP requests, but also to internal system changes.
Yeah.
So give us a specific example of why a Cloud Run service would need EventArc to work effectively.
Okay, let's say you need to trigger a Cloud Run service immediately whenever a specific critical security event happens. For instance, an IAM policy change audit log gets generated anywhere in your entire organization.
A huge deal for security.
A huge deal. You would rely on EventArc. EventArc handles the immense task of filtering through, billions of log messages and making sure that that one specific predefined event instantly and reliably triggers your Cloud Run service.
So the Cloud Run service doesn't have to constantly poll or listen for those logs. EventArc is like the dedicated centralized dispatcher for all system events.
That's a perfect description. The service can then execute a notification or maybe even an automatic rollback script based on that security alert. It connects the dots between diverse cloud services with high fidelity and speed.
Which is essential for security and operational automation. Okay, this is making a lot of sense.
Good.
So we've established the serverless extremes, functions for pure reactive code, Cloud Run for containerized serverless. Now we need to transition into a key platform as a service, or PBOS solution, App Engine.
Yes, App Engine. It's been around for a long time, but it is still one of the most powerful managed compute offerings out there.
It really epitomizes the PaaS model.
It does. We define PaaS as an environment where the vendor handles virtually everything. The OS, the patches, the runtime, the scaling, health checking, deployments, all of it. And you only manage your application code.
And to use App Engine effectively, you have to understand the fundamental architectural distinction between its two environments, standard and flexible.
This is where listeners often get tangled up.
Yeah, let's use that housing analogy you mentioned to really nail down the differences.
Okay. Think of App Engine as a highly managed private community.
I like it.
The standard environment is the prefab home.
Okay, prefab, so it's restrictive, opinionated.
Exceptionally restrictive and opinionated. You must use one of its predefined runtimes, like Go 1.12, PHP, Python 3.7. And because that environment is so rigid, the cloud provider can optimize the infrastructure to an extreme degree.
Which gives you maximum operational simplicity.
The no-ops promise delivered. And incredibly fast scaling, including that ability to scale down to 0 instances, which makes it highly cost-effective.
Yeah.
If your application requires even a single custom binary or library, you just cannot use standard.
So the lack of customization is actually the feature, because it enables that optimized speed and scaling that nothing else can really match.
Absolutely. The optimization comes from them controlling every single layer below your application code. Standard is the mandatory choice if your goal is minimizing operational overhead for a simple, stateless HTTP API with an unpredictable workload.
Provided it fits within those constrained runtimes.
Right.
And then when those constraints become too tight, we move to the flexible environment.
The flexible environment is the custom modular home. It still gives you all those high-level PaaS benefits, automatic health checking, versioning, simple traffic splitting, automated updates, but it solves the customization constraint.
How?
By allowing you to use custom Docker containers in any runtime you need. If your Python application requires specific C++ libraries, or you need a very particular configuration of some custom Java framework,
You have to choose flexible.
you must choose flexible. It requires a little more resource allocation and a bit more management overhead than standard, but it's still far, far simpler than running raw GKE or compute engine.
So the architectural choice is determined entirely by the application's demands.
That's the architectural litmus test.
If you have a standard Go API, goal is minimum management, you choose standard. But the moment you need that custom C++ library, you instantly have to shift to flexible even though you still want those managed PATOS features.
That's it. The constraint of the application dictates the environment.
So let's delve into the standard environment's optimization strategies. Let's say we're running a PHP App Engine standard service that hits a Cloud SQL database constantly. We want to minimize those expensive database queries for performance and cost. What's the platform solution?
Well, since App Engine is a closed PaaS system, you have to use the integrated services it provides. And the solution here involves platform-specific caching, specifically Memcache.
And for highly optimized performance.
You must set the Memcache service level to dedicated.
Why did it?
Because dedicated Memcache gives you guaranteed capacity and more predictable low-latency performance for your caching layer. It insulates you from potential latency spikes or contention that can happen in a shared cache pool when other applications are demanding resources.
So that reserved capacity is key for high-throughput APIs. And how do we implement this caching efficiently?
For every potential query, you generate a unique key based on the hash of the query itself.
Okay.
Your application logic then checks Memcache first, using that hash key. Only if the key is missing, what we call a cache miss, do you then issue the actual expensive query to Cloud SQL.
So you shift the load from the slow, expensive database to the fast internal Memcache service.
And dramatically improve scalability in the process.
Now let's address a major architectural limitation of the standard environment. It's aggressive statelessness.
Ah, yes.
If we have a newsfeed web service on App Engine, and during peak load, users suddenly start reporting they're seeing articles they've already viewed popping up again, what's the underlying problem there?
This is a classic symptom of confusing local state with external persistence. App Engine Standard is designed to scale horizontally and aggressively, which means it treats every single instance as disposable.
So the likely cause is that the session variable tracking which articles a user has seen is stored locally on the instance processing the request.
Exactly. The load balancer can route the user's next request to any available instance in the auto-scaling group. So the user effectively lands on a machine that has no memory of their previous session.
The platform's efficiency in scaling is actually breaking the application.
Because the application wasn't designed for a fully stateless environment. The fundamental lesson here is that App Engine forces you to manage all persistent user data and session state externally in a dedicated service like Cloud Data Store, Firestore, or Memory Store, never locally on the compute instance itself.
Good point. Okay, let's look at operational resilience. An app authentication gets updated, and suddenly its latency spikes from a few milliseconds to 30 seconds. A critical failure. What is the immediate, most crucial strategy to address this?
Operational discipline demands stability first, diagnosis second.
Right.
When unexpected latency hits production after a deployment, the priority is always quick recovery. So the prescribed strategy is roll back immediately to an earlier known good release. That stops the performance bleed.
You sacrifice diagnosis time for immediate stability.
Absolutely. Once stability is restored, then you pivot to using detailed tools like Stackdriver Trace and cloud logging to isolate the specific problem, the slow database query, the inefficient API call all within a controlled dev or staging environment.
Yeah.
You never debug live production systems under stress.
Excellent point on operational sequencing. Okay, another common challenge is security, specifically around file uploads in App Engine Standard. If users need to upload massive music files, we want them to upload directly to cloud storage without that file payload consuming our App Engine backend resources.
Right. Bypassing the backend saves compute time, bandwidth costs, and it minimizes the attack surface.
Mm-hmm.
Implementing this requires a two-step interconnected security dance.
Okay, walk us through those two steps.
First, you have to configure a cross-origin resource sharing, CRS, configuration in the target cloud storage bucket. This is the crucial step that explicitly allows the App Engine application's base URL to be an allowed origin.
So that permits the browser to initiate a direct request from the App Engine domain to the storage bucket domain.
Correct. It sets up the permission for the cross-domain transfer.
And the second step.
Second, the App Engine backend generates a secure permission slip using the Cloud Storage Signed URL feature. Specifically for uploads, it creates a signed post URL. This URL is then given to the user's browser, and the browser uses this temporary cryptographic token to post the file directly to cloud storage.
So the App Engine service never even sees the large file, but it still maintains control by generating that secure, time-limited token that authorizes the direct upload.
It manages the authorization without handling the payload. It's a really elegant solution to a common architectural problem.
It is. Now that we've seen the restrictions of standard, let's look back at flexible and how its architectural differences solve those critical network integration problems. Specifically, connecting to private networks.
This is the definitive difference between standard and flexible from a network topology perspective. The flexible environments architecture dictates that it runs inside your company's virtual private cloud, your VPC network. This is the only way to satisfy certain integration constraints.
And what constraint specifically forces the use of flexible over standard?
The need to integrate with an on-premises database that, for compliance or security reasons, must never be exposed to the public internet.
Okay.
So if your company already has a private connection, say a dedicated cloud VPN tunnel, or an interconnect to its on-premises environment.
Then since Flexible is running in the VPC, it can use that existing private tunnel natively.
Correct. The required choice is to deploy on App Engine flexible environment and leverage the existing cloud VPN connectivity. Because the flexible instances are resident within the same VPC subnet that routes traffic over the VPN tunnel, they can communicate with that private on-premises database directly and securely.
Without any extra configuration.
Right. Standard, because of its default architecture, requires an entirely different method to bridge this gap, which I think brings us to our next major operational discussion.
It does. That architectural constraint leads us directly into the most critical network challenge for serverless and PaaS solutions, the private access gap.
This is the crucial missing link for so many cloud architects. By default, environments like App Engine Standard, Cloud Functions, and Cloud Run, they all operate in managed infrastructures that are isolated from your main VPC network.
So if you have a database, a private Redis cluster, or like we just discussed, an on-premise system connected via a cloud VPN tunnel, that minimalist serverless service cannot, by default, reach it privately.
They just can't.
So we need a secure, private bridge back into our corporate network for these serverless applications. What is the essential solution that closes this gap for all of them?
The essential solution is serverless VPC access. If your company has a VPC network and wants an isolated serverless application like App Engine Standard or a Cloud Function to communicate with a private resource inside that VPC, you must configure serverless VPC access.
So how should we describe this connector? What does it actually do to the network packets?
Well, it creates a managed network bridge or subnet within your VPC. When your serverless application needs to make a private call, the traffic gets channeled through this connector.
Ah, okay.
And that allows it to send and receive packets as if the serverless service were physically running inside your VPC network. Without it, your App Engine Standard app would be forced to try and reach that on-premises resource over a public IP, which is usually impossible or just forbidden for security.
So serverless VPC access provides the secure, private egress path that's necessary to integrate serverless into any traditional enterprise environment.
It's a fundamental shift in connectivity. It ensures that operational simplicity doesn't come at the cost of security or network control.
Okay, let's widen the scope a bit to a broader infrastructure decision, one that's driven by massive, unpredictable load.
Yep.
Let's consider a scenario. A simple website, maybe a marketing landing page collecting some basic user data. It's preparing for a global campaign.
Right, the classic marketing spike.
Exactly. The projected traffic workload ranges wildly from, say, 100 click-throughs per day up to a massive 500,000 click-throughs per day. The spikes are totally unpredictable, and management wants zero operational intervention.
That's a 5,000-fold difference in daily traffic. That demands a solution that is just inherently elastic and requires minimal management.
So what combination of infrastructure is best suited for this while prioritizing that no-ops goal?
We have to choose solutions that are specifically designed for massive, elastic scalability with minimal overhead. The recommendation here is a pair of high scalability services.
And those are...
First, you use Google App Engine to serve the simple website service. Its PaaS nature, specifically its ability to scale from 0 to hundreds of instances almost instantly and manage all the underlying infrastructure. It's just perfectly suited to absorb that unpredictable burst load.
Okay, that's the front end. What about the back end, the data storage?
For that, you use Google Cloud Data Store or its successor, Firestore.
And why is Cloud Data Store the superior choice here over a standard relational database like Cloud SQL?
Because Cloud Data Store, as a globally distributed NoSQL document database, offers massive automatic elastic scalability right out of the box. A traditional SQL database requires intensive sharding, capacity planning, and manual scaling to handle a 500,000 per day load, especially if that load hits in a short burst.
But the combination of App Engine and Data Store ensures both the front-end compute and the back-end persistence layer can handle that extreme fluctuation with near-zero management.
Which satisfies the no-ops requirement perfectly. It's a powerful combination that optimizes for unpredictable scale and management simplicity.
We talked earlier about traffic splitting with Cloud Run, and it's worth reinforcing that this benefit is universal across pair solutions like App Engine as well.
Oh, absolutely. It is a core PaaS strength. If you need to test an update with a percentage of production traffic to do a canary release, the platform manages the entire load distribution internally. It simplifies the release process dramatically compared to IaaS solutions.
So the mechanism in App Engine is basically the same as Cloud Run, just applied to versions instead of revisions.
Precisely. You deploy the new code as a new version within the existing App Engine application. Then you just use the App Engine traffic splitting configuration to divert, say, 10% of incoming requests to that new version. The load balancer, health checks, request routing, it's all managed automatically by the PaaS layer.
Which ensures the test is contained, safe, and easily reversible.
By just routing 100% of traffic back to the old version.
All right, we've spent most of our time at the minimalist, managed end of the spectrum. Now let's swing back to the maximal control side. Compute Engine and Google Kubernetes Engine.
Where complexity increases, but so does your flexibility.
Right. And Compute Engine, or CE, is fundamentally where many enterprises start their cloud journey.
It is. It facilitates a rapid lift and shift where they just take their existing virtual machine images and move them to the cloud.
Yeah.
It's maximum control. You decide everything. But it brings that maximum operational burden.
It's a necessary bridge, but it shouldn't be the long-term destination.
Exactly.
So if a company has successfully lifted and shifted their legacy VMs to Compute Engine, but now they need to design a more strategic, auto-scaling, and no-ops solution over the next 6 to 9 months, where should they be targeting?
They need to target highly automated self-healing platforms that minimize that day-to-day burden of patching and scaling. And the two recommended strategic targets are Google Kubernetes Engine, GKE, using containers, or Google App Engine standard environment.
So those are our two paths to modern automation. GKE provides that sophisticated orchestration for customized containers, and App Engine standard provides maximum opinionated simplicity.
And both are far superior to managing individual Compute Engine VMs manually. It's a move from IaaS, which is a compute engine, to an advanced PaaS Orchest model.
Container as a service.
Right. And the choice between GKE and App Engine depends, again, on those application constraints we discussed earlier.
Okay, so let's talk about the specific constraint that forces us to GKE. When serverless or PaaS simply cannot do the job and you need that absolute control.
This constraint is almost always the requirement for state persistence.
State.
Most serverless environments are aggressively stateless by design to facilitate that rapid horizontal scaling. But what if you have a legacy application, maybe an aging enterprise messaging service, that uses a local file system for session data, and the application requires that state to persist across restarts and scaling events?
That application is inherently stateful. If you scale it horizontally, instances will die and come back up, losing their local memory and disrupting user sessions.
It just won't work.
So you need container flexibility, but you also need the ability to attach persistent, reliable storage.
The only robust solution for deploying a legacy stateful application in a modern containerized environment is Google Kubernetes Engine, GKE, using stateful sets and persistent volumes.
Okay, explain the mechanism of a stateful set for us. How is it different from a normal deployment?
A standard Kubernetes deployment treats all its replicas as interchangeable and disposable. A stateful set, however, is designed specifically for stateful applications. It ensures that each replica of your application has a stable identity.
The stable identity.
Yeah, including a unique stable host name and, critically, a corresponding persistent volume claim that ensures dedicated storage follows that replica, even if it gets rescheduled to a different node in the cluster.
So it's like assigning a specific labeled locker, the persistent volume, to a specific container, the replica. If the container moves, the locker moves with it, ensuring the session data is never lost.
Exactly. This provides the necessary control over storage and state persistence. It allows that legacy application to benefit from Kubernetes orchestration and auto-scaling, while satisfying its fundamental requirement for local, persistent storage.
Which is something impossible in the App Engine standard or Cloud Functions models.
Impossible.
That firmly establishes GKE as the architectural choice for applications demanding both customized containers and state persistence. Finally, let's tackle an expert-level networking challenge: advanced API management.
This is a complex scenario, but it's really common in large enterprises. You have completely refactored your API, creating a new V2 version, but you must maintain the old V1 version for existing clients for several months.
Okay. And the catch?
The catch is that both the V1 and V2 APIs must be accessible via the same SSL certificate and the same DNS records. For example, api.yourcompany.com.
So we can't use two different host names, and we can't use two different load balancers because that domain name needs to resolve to a single public IP. How do we route traffic internally based on the API version the client is asking for?
This is a pure load balancing and network routing solution. The required action is to leverage the global load balancer's capabilities by using separate back-end pools for each API path.
Explain how that path matching works in this context.
Okay, think of the global load balancer as a central hub, or maybe a hotel's front desk. It receives all incoming requests on that single public IP and SSL certificate. You then configure URL maps that perform path matching.
So you're looking at the URL itself.
You create a rule that says any traffic hitting the URL path EP1 is directed to backend pool A. And backend pool A points to your V1 compute endpoints, maybe a set of App Engine standard services or Cloud Functions.
And at the same time,
Simultaneously, you configure another rule that says any traffic hitting AP2 is directed to backend pool B, which points to your new GKE microservices or Cloud Run services.
so the client just requests api.yourcompany.com/BOV1 users or .apv2 users, and the load balancer intelligently routes them to the correct versioned compute environment behind the scenes.
All using the same single public endpoint. It solved that simultaneous versioning challenge at the network layer, decoupling the public interface from the underlying compute architecture. It's a powerful, flexible, and extremely scalable way to manage API migrations.
And that, I think, completes a truly comprehensive deep dive today. We've moved all the way from the pay-per-use economics of Cloud Functions to the stateful architecture required for GKE stateful sets.
The primary lesson we have to reinforce is that the choice of compute environment is always an informed trade-off. It's dictated by explicit constraints.
Right.
Are you constrained by cost sensitivity and spiky use? That pushes you towards Cloud Functions or Cloud Run. Are you constrained by needing custom code or specific C++ libraries?
Yeah.
That pushes you to App Engine Flexible or potentially GKE.
So let's synthesize the clear distinctions for everyone one last time.
Okay. Serverless, functions run. Pay-per-use, scale to zero, event-driven processing. And remember, Cloud Run adds that container flexibility and the simple internal traffic splitting for canaries.
App Engine Standard. Maximum operational simplicity, strong PyASYS features like versioning and traffic splitting. It's the speed king, but its isolation means it requires serverless VPC access to communicate privately with internal networks.
App Engine Flexible, all the paths and benefits, plus custom Docker container support. And because it runs within your VPC, it's the required choice for applications that need to leverage an existing cloud VPN or interconnect to reach on-premises resources privately.
And finally, GKE Compute Engine, maximum control. Compute Engine is the lift and shift starting point. GKE is the chosen solution for stateful applications, using stateful sets and persistent volumes to ensure data persistence. That's its architectural differentiator.
Understanding these architectural drivers state, custom requirements, cost, network topology, that's what allows you to move beyond just product names and really speak the language of cloud architecture.
That is a phenomenal architectural framework to start with. Before we wrap up, let's leave you with one final thought to mull over, connecting back to the operational benefits we discussed.
We saw how Cloud Run and App Engine manage traffic splitting for canary deployments with impressive simplicity. Now, consider a scenario where your company needs to roll out a major breaking API change over 6 months. The requirement is to slowly shift exactly 1% of production traffic every single week, moving from V1 to V2. And then you have to maintain that precise split, say 94% V1, 6% V2, for another 3 months for testing and observation.
So which of the platforms we discussed, App Engine, Cloud Run, or a manually configured GKE behind a load balancer, provides the simplest, most operationally light way to manage that minute ongoing traffic configuration change over that protracted 9-month period.
Right. Think about the operational friction of repeatedly logging in to manually adjust percentages versus relying on the automated declarative configuration of a managed POS feature.
It really highlights the true value proposition of POS.
It's not just about scaling. It's about abstracting away complex, repetitive operational tasks.
Thank you for joining us for this deep dive into the world of cloud compute. We hope you walk away better equipped to answer that fundamental question, why you use what you use.